Hello, I'm Robert Davies, a physicist with the Utah Climate Center. And let me start by saying, if this is how you feel when the topic is climate change, you're not alone. And you have every right to feel that way. The volume of confusing and conflicting information is staggering. What I'm going to try to do then in the next 15 minutes is cut through some of that noise. To do that, I'm simply going to summarize 4 things that science knows about the climate change that's occurring currently and the additional changes we might expect in the coming decades. And the first thing we know with high confidence is that Earth is warming globally. This is what that warming looks like from the end of the 19th century to the middle of the 20th to today. Now we'll look at this again, but what you're seeing as the different locations on the map change from the cooler blues to the warmer reds is warming of those locations, and the more the change, the deeper the red. From the end of the 19th century to the middle of the 20th to today. Now, 2 things make themselves very clear in this data. The first is that the entire planet is warming, and the second is that warming is not uniform. In particular, we see the higher latitudes in the northern hemisphere, the northern poles, are warming faster than the rest of the planet, and the land surfaces are warming faster than the oceans. If we average all of the locations together, we find that the planet as a whole has warmed about 1 degree Celsius in the last century or so. Now that may not seem like a lot. I'll put it into context in a few minutes, and it turns out to be quite significant. And for those of you metrically challenged, I apologize. You can convert a change in temperature from Celsius to Fahrenheit by roughly doubling it. So this is about a 2 degree Fahrenheit global average temperature change. Another way to look at this data is to plot a change in temperature for every year for the globe going back 130 years or so. And if we do that, it looks like this. So again, we're looking at temperature change. We're plotting it relative to the mid-20th century average. And when we do that, we can see the very clear temperature trend over the last century or so, from the cooler years in the early 20th century to this continuous progression of record-setting years in the late 20th century, right up until the warmest year on record, which was last year, 2015. So this is what we mean by global warming. Now the second thing we know with high confidence is why the planet is warming. And not to put too fine a point on it, but it's because of us. Specifically, this planetary warming is being driven by the carbon dioxide that human civilization is emitting into the atmosphere, principally from the burning of fossil fuels. As a result of these emissions, carbon dioxide levels in the atmosphere are increasing, rising nearly 50% over the last 200 years, but most of that rise coming in just the last 50 years depicted here. Now, this rise in atmospheric CO2 is important because carbon dioxide is a greenhouse gas. And because of their molecular structures, greenhouse gases, like CO2, methane, even water vapor, absorb energy that is leaving the Earth in the form of light and convert that energy into thermal energy, warmth. That means energy that used to be escaping the Earth system is now being trapped instead, and that means the planet warms. This then is what we mean by the term anthropogenic global warming, caused by humans. Now the third thing we know, again with high confidence, is that the ongoing and accelerating human-driven global warming is disrupting the entire planetary climate system. And this is because when you change the temperature, everything else changes. Everything's connected. Warmer air, for example, holds more moisture. So raising the temperature intensifies evaporation, and dry places tend to get drier. At the same time, when you do get a storm, there's more water in the air to come down, and so precipitation also intensifies. Now combined, this increased evaporation and stronger precipitation is what climate scientists call an intensification of the hydrologic cycle, and by itself already represents a profound impact to the planetary system. But this impact only scratches the surface, because as I said, when you change the temperature, everything changes. Ice sheets, tundra, glaciers, snowpacks across the planet are melting. Sea levels are rising, sea chemistries are changing, soil chemistries are changing. Changing the planetary temperature changes where it rains and where it doesn't, where it snows and where it doesn't, where things grow and where they don't, where critters live and where they don't, and on and on. Everything changes. And this is what we mean by the term global climate change. All of these changes, in turn, are already having a profound impact on global ecosystems, and all of these changes, in turn, are impacting human systems, which are completely immersed within the Earth system. There are now observable impacts to food, water, health, transportation, economies, even political stability. In many cases, these impacts have been significant, even severe. Here in Utah, where temperatures have been rising at nearly twice the global average, as evidenced by records from all around the state, we are seeing impacts as well. And these include a shift to higher extreme temperatures, reduction in springtime snowpack, changes to ecosystems such as bark beetle infestations, and a trend toward bigger and hotter wildfires, to name just a few. So, we know the Earth is warming. We know this warming is primarily the result of human carbon emissions and principally from the burning of fossil fuels, and we know this human-driven global warming is disrupting the entire planetary climate system. And this is why I don't get invited to parties anymore. The fourth thing that we now know with high confidence is that continuing this climatic disruption brings with it extreme risks for humans. And this knowledge arises from our observations to date of the impacts to both natural and human systems, some of them already severe, and then using models to project how much more warming and subsequent climate change we can expect in the coming decades. Now, this topic of modeling can be quite complex, so a couple of clarifications. First, these are not the models we're using to help us better understand the climate system. No. Instead, the term model here simply means physics, and not climate physics, just regular old physics, the same physics that allows us to build smartphones and microwave ovens, but applied to the climate system. Now, second, the question is often asked, are the models right? And we have a definitive answer for this. No. In fact, we know that they're wrong. That's because we don't know everything. But there are different degrees of wrong, and not knowing everything isn't the same as not knowing anything. So while these models cannot precisely predict every aspect of the changes ahead, they are helping us project or bracket a range of possible futures. So let's take a look at what the physics is telling us. With respect to temperature, the models give a considerable spread of possible warming by the end of the century. From a 4-degree Fahrenheit rise here in Utah, for example, to as much as 15 degrees by the end of the century. And such a wide spread of possibilities reflects quite a bit of uncertainty in the projections. And it tempts one to think that the modeling really isn't very good, but in fact, most of the uncertainty in these projections is not from an uncertainty in the physics, though there is certainly some of that, but is because we don't know how we humans will choose to move forward. And so we have to actually model different scenarios. If we choose to move aggressively away from fossil fuels very soon, that's a low carbon scenario, and we expect a smaller temperature rise. On the other hand, if we choose to continue burning fossil fuels as we have been, a high carbon scenario, then a more extreme temperature rise becomes much more likely. Now, it may not seem like it, but this is good news. It's good news because the physics is telling us that the changes in front of us, and therefore the level of risk that we face, is entirely up to us. To put this scale of change into perspective, I've constructed a little thermometer in Fahrenheit. You're welcome. On the left, 45 degrees Fahrenheit, Earth's temperature at the depth of the last ice age. On the right, 75 degrees Fahrenheit, the warmest we believe the planet has ever been, about 55 million years ago. The green oval is the climate in which we humans evolved and have always inhabited. The region between the two lines is the climate in which human civilization evolved and has always existed. The purple oval is the climate to which we can expect to transition this century if we do not take meaningful actions. The point of relevance, of course, is that the ovals do not overlap, even on the low emission scenario. In other words, we are in the process of leaving the human climate. To further convey a sense of the choice before us, let me show two more projections of regional interest. And what we're looking at here is spring snowpack, March and April, in the Rockies, when our snowpack has typically been at its maximum, ready to start filling the reservoirs. I'll focus you here on the part of the Rockies around Utah, and point out that when we get to the light gray, it's very low snowpack, darker blue is deeper snowpack. We'll start with snowpack observations over the last 60 years, followed by projections for the next 85 years under a high carbon emissions scenario. Again, the scenario we're currently following. So here are how observations of snowpack evolve since 1950. And we see that there's considerable variability to the springtime snowpack, but we always observe a pretty deep snowpack. Now we're moving into projections. The snowpack in the springtime is decreasing, and as we moved past mid-century, we find it has essentially disappeared. These projections are particularly relevant to those of us here in Utah because most Utahns get most of their water from melting snowpack. Also of high importance and interest is soil moisture arising from a combination of temperature, precipitation, and vegetative cover. Now this projection looks at the evolution of soil moisture through the 21st century, first under a moderate emissions scenario, where deeper browns mean more drying. We see significant drying across most of the U.S. and Central America through mid-century, stabilizing afterward as carbon emissions presumably come down. The situation is different under a high emissions scenario. Again, significant drying through mid-century, followed by dramatically intensified drying in the second half of the century. The agricultural scientists, ecologists, and economists who assess these results often categorize the moderate emissions scenario as dangerous, and the high emissions scenario, again our current path, as catastrophic. So, projections of rising temperatures, melting snowpack, intensification of the water cycle, drying soil, and all the rest. This brings us to the point of interpreting this science from the standpoint of risk. Now, I've already stated that science has assessed the risk to humans as extreme. Now, here are quotes from two prominent climate change scientists that underscore this point. This is Lonnie Thompson, a distinguished glaciologist, and Kevin Anderson, one of the world's preeminent carbon modelers. Their words, clear and present danger, incompatible with an organized global community, may seem extreme or even shrill. I'll simply state that these sentiments are common within the climate change science community. To review then, these are the things that science understands with high confidence about climate change. The planet is warming, driven by human activity, principally the burning of fossil fuels. This global warming is driving a planetary scale disruption of the climate system, climate change, the impacts of which are already pronounced, and our current trajectory of change poses extreme risks for humans. All of this said then, there is one more piece of knowledge that seems necessary. Does science have anything to say about managing the risk, which is to say mitigating further change? The answer is yes, and the simplest way to frame it is this. First, additional disruption of the climate system is directly tied to how much additional carbon we dump into the atmosphere. More carbon, more risk. Second, physics can estimate a dangerous level of planetary warming beyond which risks to humans rise sharply. We currently believe this level to be an additional 1 degree of warming for a total of 2 degrees Celsius. Finally, physics can calculate a carbon budget, which is to say how much more carbon we can put into the atmosphere and maintain a reasonable chance of staying below this dangerous level of warming. And here is that budget. It's about 900 billion tons of carbon. And here's how fast we'll exhaust this budget on our current pattern of consumption. About 2 decades. And finally, here is that budget relative to humanity's known reserves of coal, oil, and natural gas. And so what physics has to say about mitigating our risk is that we must stop dumping carbon into the atmosphere, and we must do so soon. To do that, we must move aggressively away from fossil fuels. Specifically, the physics says we can only burn about a quarter of our fossil reserves. And the state of the science then is this. Dangerous climate disruption is currently underway. Without meaningful response, catastrophic climate disruption is probable. and our window for achieving this meaningful response is about 2 decades. I'm Robert Davies with the Utah Climate Center. Thanks for listening, and we hope this has been helpful.